Thank you very much. Just a bit of background about myself and our company. So OMAR ALAOUI, I'm working as marine civil specialist with ADNOC Logistics and Services. It's a group company, part of ADNOC. We mainly operate in all ADNOC oil and gas fields. We do offshore logistics, offshore supply, marine services, offshore projects as well, EPC. We do also marine civil projects, and one of the biggest projects that we recently completed is, as maybe some of you might know, ALAOUI Island, Island G, which is the biggest energy island within ADNOC oil and gas fields, part of the Lower Zakum oil field. We also operate in shipping, LNG, oil, gas, bulk, and other petrochemicals. We do survey as well and the other services, mainly for ADNOC group companies. So our topic for today will be, let's say, a revised approach based on recent development in Eurocode 7 and Eurocode 8, applied, and I try to tailor it to artificial energy islands. As you know, artificial islands, especially for energy and also for real estate and mixed use, are not simple construction, dredging and reclamation, ground improvement projects. They are, in our context within ADNOC, strategic assets that host critical drilling, process, non-process accommodation, dewatering power plant assets. Therefore, I mean, the performance of the reclamation itself becomes really important to manage, not only during execution, but also after execution at handover and during the full life cycle of the project itself. So, at the moment, currently, as you know, I will just present quickly the standard practice. The projects start by sourcing the material, the sand, whether from the vicinity of the project itself or from a specified, let's say, borrow area. And for that, when the material is being transported, it undergoes laboratory tests, gradation, carbonate, shell content, unsuitable material screening, etc. Then at the hydraulic feeding stage, we decide on the placement method, and also when to start bottom door dumping, when we do rainbowing, and when we do pumping. And then for that, during the reclamation, when we start seeing the sand, we do also some basic QC tests and boreholes, etc., to understand the quality of the material. After that, once we have a platform and we are ready to do ground improvement, we start the ground improvement by deep ground improvement. In our area here, we talk mainly about circa 20 meters of reclaimed land, reclaimed platform, which requires deep compaction techniques. We start by, mainly we do vibro compaction. And then we use also dynamic compaction in some cases if the depth is shallower, or if dynamic compaction is required at certain shallower depth. Then at the top we do the surface compaction. Then after that the QC process required to do the post-treatment verification using mainly CPTs and borehole CPTs for the quality of the ground improvement. And also the type of soil behavior type, and boreholes to check physically the content of the material. And at the end, as client or as contractor, hands over a factual report with all the NCRs that were closed out and all the data that has been gathered during the project. this process comes, has or present many challenges. It's not as simple as that, especially when you are dealing with natural material, dredged from a source, and reclaimed in certain way. So these challenges are are different between different involved stakeholders and at different stages of the project. In our case, we use the value assurance processes at the define stage. The client finds problems sometimes the client or asset owner finds let's say challenges in defining translating, let's say, the performance requirement into specifications or scope of work. The consultant at the define stage, which is basically the feed in our case, sometimes feed to the detailed design level, has limited data, has uncertain field sources. He doesn't know how the field would look like. It's a heterogeneous field, and he is not necessarily sure of the loads. The contractor at the tendering stage doesn't receive the specifications, so he doesn't know how to approach the platform and how he will be able, or whether he will find any obstacles during the execution. At the execute stage, the client or asset owner or asset representative or the developer, in some cases in Abu Dhabi and Dubai, etc., the client has issues, with local non-compliances, usually due to siltation, due to inability to achieve certain performance, which becomes later dispute during the execution or after handover with topside. In our case, in energy islands, dispute with topside contractors and asset owners. Consultant always enters into debates in terms of when defining CPT interpretation methodology, especially for the carbonate sand that we have here in the region. And the contractor struggles to have a full depth CPT that is fully compliant, and the reclaimed field that is also fully compliant with specifications that were written at the defined stage, especially in the context of an offshore project where the contractor sees the 4 seasons basically, has downtime sometimes and has some site constraint during the construction. At the operate stage, the client or asset owner finds it difficult to follow up on what happened, and he doesn't have, let's say, a model that he can, let's say, established model that he can use to see what was done and let's say update during throughout the design life or life cycle of the project. So basically all the data in Excel, in PDF, etc. is lost or archived. The consultant at handover basically, or the reviewer, let's say, not necessarily the same consultant, might find it difficult to compare the as-built ground behavior or as-built ground quality with the design assumptions. And the contractor might go into dispute and claims due to inability to resolve the site, let's say, quality problems, which are not necessarily performance issues. So, in order to address these challenges, we thought about using basically recent advances in the Eurocode 7 and Eurocode 8 and local practice as well and experience to let's say, link all the tasks, let's say, that impacts the design of these energy island platforms together and introduce new concepts basically as compared to previous requirement on whether a certain CPT line met exactly the requirement or not. So basically turning from whether we met the certain density to whether the function of the platform has been fulfilled. So basically this framework starts from defining a suitable basis of design at the defined stage by the consultant, between the consultant and the client, then developing a ground model at inception stage, task studies, which in this case, as compared to previous revisions of your code, the ground model was not central in the assessment. At the moment, it's becoming central and it has a value. So the ground model, I will come to the definition of, I mean, some of you or most of you maybe know already these definitions, but I will come to them in more details in the upcoming few slides. Then developing a geotechnical design model, which caters basically or includes the representative values of that will be used, whether at the original seabed level or the values that were used to design the platform itself that will sustain the topside loads. So then defining the performance verification that need to be carried out depending on the limit state, not same checks for everything, for all zones. This is something that I don't want to see anymore, I mean, in our industry. Then working on the implementation of the design. So at the define stage, the designer with the client and probably early involvement from the contractor sits together and prepare already inspection, monitoring, maintenance plans suitable to achieve their required performance. And then agree on life cycle on let's say what needs to be done to manage properly the life cycle of the platform at the operate stage. So the objective is not only from this framework is not only to demonstrate that the reclamation specifications have been met, as I said, but to prove that each platform zone can safely and reliably perform its intended function. So the first thing, I'm just taking some snaps from Eurocode for quick reference. First thing to start with is to define the design life of the structure. The moment we are working with 50 years, some structures, they are designed for 100 years, but what we are using in general, it's 50 years for these energy structures, platforms. Second thing is defining the consequence classes, consequence of failure. So consequence going from for geotechnical systems, this goes from 1 to 3. It goes up with the higher consequence of failure. And we have CC1, CC2, and CC3 depending on the type of structures. In general, for our structures, we would probably go with CC2 for the reclaimed platform for normal areas. But if the platform has critical structures, that might mean that we select CC3. Or it's in the interface with the critical, let's say, structure. Then we define geotechnical complexity classes, basically, which is the level of uncertainty and the complexity in the ground conditions and ground structure interaction. In our case, most probably it will be around GCC2. As the reclamation, I mean, at macro level, it can be seen as uniform, and the ground conditions that we have here are also quite uniform, at least in offshore Abu Dhabi, and I think it's same in Dubai. So this geotechnical complexity class links ground uncertainty to the required level of investigation, interpretation, verification, and rigor in controlling the works. Then from the consequence classes and geotechnical complexity, we select the geotechnical, let's say, category of the asset. And this geotechnical category, as you can see, it goes from 1 to 3 as well. It combines both the consequence of failure with the complexity of the ground conditions, and also it is being used to determine the required level of investigation, design, verification, execution, control, independent checking, and monitoring. And this can be different within one same project. I mean, that's the idea. It's not the same for the whole project. We have some areas that are just lay down areas, corridors. We have some process areas with the pipelines, supporting pipelines, let's say, and we have some areas where we have drill pad, and we have some areas that are interfacing with the quay wall. and other critical structures. So in one project, we might have different zones. And that's, let's say, basically the beauty of this proposed revised approach, and which will mean at the end to reduce the debate between the client and the contractor, and at the end hand over the project safely to the asset owner or operator. Yeah, so basically more details on the geotechnical category. It measures, it shall be used to specify the extent and amount of the following measures: measures to achieve appropriate representation of the parameters, measures to achieve the accuracy and validation of the calculation models. I mean, it can be, we might need much more modeling. We might need, 3D modeling in case of higher class, let's say, geotechnical class. We might need just simple calculation in case of GC1, for instance. But this is in a structured manner. It's not left to subjective opinions of different stakeholders within the project. Measures to prevent the errors in design and execution, and measures to ensure appropriate implementation of the design according to the specifications, which are also part of the Eurocode, in terms of supervision, inspection, monitoring, and maintenance effort. Then we move to the seismic design. We classify also, let's say, based on the consequence class, we can calculate seismic action index and find out whether we are in a very low, moderate, or high seismic action class, which means if we are in very low seismic action class, or we might not need to use Eurocode 8 at all. And if we are in the low, let's say, seismic action class, we might also use simplified methods, seismic design methods, instead of the recent proposed methodology. They are also, the delta is also important to help defining the ductility classes for the structural design, and also the level of verification that is required during the seismic design of the reclaimed platform. Then we go to the limit state, which is the state of damage of geotechnical systems. I mean, in our case, we have at the moment one single, let's say, kind of one single check or set of requirement that applies everywhere. It will be more beneficial to define, limit state that needs to be checked, because every limit state in this case will come with different input, with different acceleration, and we require different verifications and control during execution, and handover requirement. So in some cases we might just need to choose a significant damage check for lay down areas. In other cases we might need to check for both. In all cases, for the Eurocode 8, we need to comply with we need to pass the significant damage check in all cases. And another note, for the platform, the seismic action and the action associated to each specified limit state should be the same as for the topside structure. So we cannot be in a lower, check for a different or lower, let's say, class. Then the return period, that's something that is also very important in the recent second generation Eurocode 8, part 1.1 and part 5, where we have a clear methodology to select the return period based on the limit state that we are checking for and the consequence class. So in one project we might have different checks, not one PGA everywhere. And this might help also streamline some discussions and difficulties that client and contractors and consultants are finding during the projects. So for instance, the previous Eurocode was mainly referring to 475, if I remember, which corresponds to a 2% probability of exceedance during the 50 years design life, which is something that we are using. 10%, sorry, not 2%. And in energy project, in our project, we use usually 2,475, and it was basically without clear basis. Now we have a clear basis. We might use it only for critical areas, not everywhere. which will help everyone, I mean, during this, this project, and also help the asset owner, or let's say the client, control and reduce debates during the define stage and the execution stage. Then we move to the ground model, which shall be developed comprising geological, hydrogeological, geotechnical conditions, the site based on the ground investigation result. At the start of the project, where there is no ground investigation result, we use the available information and previous experience. Then the details of the detail level of, and extent of the ground model shall be consistent with geotechnical category. That's something very important. So if we are talking about geotechnical category, number one, I mean, we don't need to have a lot of details. Number two, more details. Number three, we move between number 2 to 3, we move to 3D digital terrain, using GIS, using advanced techniques due to the complexity, basically, and consequence of failure of the structures. And this helps as well, having, let's say, comprehensive view of what is happening in our project. The ground model shall be progressively developed and updated at all stages based on potential new information, also during construction, not only during design, stopping during design and forgetting about what was the ground model during design, but during the construction as well. When reclamation comes, then we add it, and we add the data from the boreholes and CPTs and lab tests. And then after operations as well, we monitor settlement, etc., and we feed it into the ground model. The ground model is constituted of, includes the derived values from the investigation of the ground properties, basically. Then we have geotechnical design model that is built based on the ground model itself, and includes the representative value of the ground parameter. Unlike the first generation, where we were talking only about characteristic value, which is a statistical value from the test, the geotechnical investigation and test. Now we talk about characteristic value and nominal value. So mainly characteristic value is a statistical value based on the statistical evaluation, and the nominal value is a value that can be selected based on engineering judgment in case of lack of sufficient data to inform the geotechnical design model. So for the
Engineer Omar, just 2 minutes more, please.
2 minutes more?
Yeah, please.
Okay, so I need to go quickly. So as I said, geotechnical design model shall include representative values. Then we move to the implementation of the design, which is something important that was introduced in Eurocode 7, which asks the consultant and the client to develop together supervision, inspection, monitoring, and maintenance plan instead of leaving it to the contractor during the execution stage. It can be initiated at the defined stage and elaborated, let's say, during the execution stage. Then we have the performance verification for that needs to be defined as well during the defined stage. That includes the material and ground improvement verification, field stability, field quality, etc. Platform performance verification, settlement bearing capacity, liquefaction, settlement, differential settlement bearing capacity, and so on. Then we have the seismic design and edge stability verification, which includes liquefaction, lateral spreading, post-liquefaction deformation, key wall revetment, harbor, interface stability, etc. And residual stability for selected limit states. All these are being verified, used at the moment, but they are not being tied to the consequence classes and limit states and all details that I have presented before. So, as I said, for the performance verification, very important. It's introduced by Eurocode 7, or recommended by Eurocode 7. We should be using statistical, let's say, evaluation instead of single values, which is something that is being used at the moment. Which might also mean that we need to increase the testing density in our project. It's not relaxing the requirement, but maybe increasing the requirement in terms of testing, and then using the statistical analysis. And it should be split by zone and depth interval. So it's not something that applies everywhere, and horizontally or vertically. So example that I will just give you an example for energy islands. As you can see, I tried to apply this proposed framework or proposed device approach based on the recent Eurocode and let's say experience in energy islands. So for two zones, Zone A, which is offshore facility core, and Zone B, which is logistics and laydown area, the consequence class can be different. CC3, there's a difference between CC3 in the seismic code, CC3A and CC3B. CC3B is more, let's say, stringent. It can be applied for nuclear power plant project and highly critical project, and the return period for this can go up to 5,000 years for the PGA. In terms of geotechnical complexity, we have two different geotechnical complexities. Zone A is much more, might be much more complex. We might have the same if the soil is uniform. It depends on the ground information. Geotechnical category, we end up with two different geotechnical categories instead of one geotechnical category in previous project within the same, let's say, island. The main limit state that needs to be assessed is significant damage, as recommended by Eurocode. But for the Zone A, we might need to go to check in the near collapse prevention. And for Zone B, we might also do the damage limitation if serviceability matters. And then we have the checks that need to be defined by the consultant, I mean, together between the consultant and the client at the defined stage, the checks for each limit state. So they shouldn't be not necessarily the same everywhere. Definitely the criteria, the tolerance, the criteria, the maximum acceptable performances will be different depending on the limit state. And then the verification intensity during the execution, it is something that is also well defined in the Eurocode. Not necessarily for reclaim the energy island, which is something that we can work on. We are now hopefully starting this discussion together. So for geotechnical category number 3, we might need a proper full 3D GDM and calibrated CPT for carbonates and etc. A dense grid and maybe enhanced monitoring during and after the execution of the project. And this is something important because some issues happen actually during these operations, with huge drilling rigs. And for Zone B, we end up with a zone-based GDM, maybe simplified, normal statistical CPTs with normal assumed, let's say, correction factors, slightly coarser grid, and periodic monitoring. Then, that's the slide before the last slide, just for information. And then in terms of seismic bases, that's where it gets also interesting. For the same project, for Zone A and Zone B, we have, for using a reference PGA of 0.05 G, for instance, at 475 year return period, we end up with a return period for significant damage check of 800 for Zone A, depending on the consequence class, and 475 for Zone B. So we will have different, let's say, horizontal acceleration to check for in liquefaction, all other seismic-induced settlement, and all other seismic analysis, seismic being capacity, etc. So which will mean 0.09 G for the Zone A and 0.025 for the other for Zone B, which makes a huge difference. Why it makes a huge difference? Because when we build these artificial islands, we need land to operate from during the. I mean, we work for 1 year and we don't see anything. And we need land as soon as possible to start operating from and to put the camps, etc. And if you are still struggling to achieve the performance requirement or due to multiple reasons, debates that are ongoing, you will still wait for the approval of this area before being able to use it or hand it over to someone else. So it is very important, and this land is very important because without land you have accommodation barges that cost a lot per day. You are using marine equipment that costs a lot per day. That's during execution, and you would have also different checks probably, and that are probably different in terms of complexity and requirement in terms of numerical modeling and 3D modeling and soil structure interaction probably in some cases. Whereas in the Zone B, you would probably use normal empirical equations to do settlement, bearing capacity, liquefaction screening, and long-term settlement as well. So Just to give you an example, this is one of the energy islands that belongs to ADNOC offshore. That's a public picture, by the way. It's not nothing internal. Here, for instance, you can see the process area, the process and the drilling area with the drilling crane and the pipe racks, etc. This area, for instance, can be classified, in our case, based on this framework, as, sorry, this is not the conclusion slide, I just remembered. Sorry for that. That it can be classified as differently as compared to an area that is just constituted of lay-down areas, corridors, and roads. Takeaways in conclusion. So this proposed framework basically tries to reframe, by this framework, I'm trying to reframe reclaimed energy island from just compacted and filled, let's say, platforms into classified geotechnical assets or geotechnical systems and assets that are designed, verified, and operated by zone, by function, and by life cycle requirement throughout the life cycle, which means for the owner and asset manager, clearer performance requirement, better handover, monitoring basis, and thresholds for the life cycle risk visibility if you want to do digital twinning and manage the asset. For the designer and consultant, it means structured use of classification in a structured way, ground model, ground design model, representative values in a clear way, clear method, and limit state, and the clearer specifications that gives a way to everyone during the execution of the project to find a solution. For the contractor, reduced ambiguity, clear acceptance criteria, and ways to solve the issues during the works, where we don't focus on certain lines, but we focus on achieving the function. And for the operations, better link between the as-built ground behavior, settlement monitoring, seismic performance, and future modifications. So he will receive this geotechnical design ground model basically, and he should keep it and update it throughout the design life of the project instead of receiving just Excels and PDFs, etc., and of the data. Then, in terms of governance and assurance, this assures that's something very important. That assures that we have traceable design decisions from the defined stage until the handover and operation, risk-based verification efforts that were done and undertaken and justified, and auditable acceptance logic at the end of the project. That's it. Thank you very much, and I hope you appreciated the presentation.